The goal now is to find equations of planes in the 3 space. Before we do that, let's recall how we can find the equation of a straight line in the 2 space. So you'll see that that a plane is basically an analog of a straight line. So recall that to write down the equation of a line, we need a known point on the line and its slope. How do we find the slope of a line? Well, given a line, we pick 2 points, x1, y1, x2, y2 on the line, and then the slope is given by y2 minus y1 divided by x2 minus x1, which is known as the rise over run. Now, what does the slope measure? Well, the slope of a line measures how steep the line is with respect to the positive x-axis. So if I draw a line, so as I move it toward the positive y-axis, the steepness is increasing. Another way of looking at it is that the slope is measuring the angle of inclination between the line and the positive x-axis, which is theta. The question now is, how do we come up with the equation of a plane in the 3 space? Well, is it possible to define a slope for this for a plane? Well, first of all, when we looked at we know that in dimension 2, the slope of the line is measuring the steepness of the line with respect to the positive x-axis. Well, the problem is, if we are measuring some sort of steepness of the plane, I mean, steepness of the plane with respect to what? With respect to the positive xy plane, the yz plane, or the xz plane? Which one? Another difficulty here is, notice the way we defined the slope. It was we defined the slope by just in terms of just 2 points on the line. Now, how do we go about finding the slope of the plane by just picking points on the plane? So you see that there is a bit of a difficulty in defining the slope for a plane. It's not clear how we should go about it. So we're going to take a different route in finding the equation of a plane. And before I do that, I'm going to show you first a new way of finding the equation of a line. That is, we're going to still need a point, but instead of the slope, we're going to see is that we can instead of the slope, we can work with a vector perpendicular to the straight line. So let's look at a line L. Then the equation of the line has the form ax plus by is equal to c, where a, b, c are constants. If I set n to be the vector ab, where a and b are coefficients of x and y respectively, then what I want to show is that n is perpendicular to the line. In order to read off the coefficients of x and y here, we need to make sure that x and y terms are both on the left hand side. Now notice that for example, if I have 2x minus 3y is equal to 0, this straight line here, then the perpendicular vector n is going to be 2 comma negative 3. Now, so my goal now is to show that the vector AB is perpendicular to the line L. Recall that two lines L1 and L2 are perpendicular if and only if the slope of one of them is equal to the negative reciprocal of the other one. So if m1 is the slope of L1 and m2 is the slope of L2, then L1, L2 are perpendicular if and only if m2 is negative 1 over m1. Okay, so let's now try to prove this fact. Okay, so we have the straight line L. It has the equation ax plus by is equal to c. And if I solve for y, then I'm going to get negative a over by plus c over b. Now we see that the slope of the straight line L is then negative a over b. Now if you look at so let's say the vector n with components a, b is given by this green vector. Then what's the slope of this green vector? Well, the green vector passes through the origin here. I'm drawing the vector n. We are drawing the vector n with tail at the origin. So this is this you can think of that as this straight line between the point AB and the point 0, 0. So then the rise over run would be b over a. So the slope of this green vector, or the vector n, is b over a. So we see that the slope of the vector n is negative reciprocal of the slope of the straight line L, so they must be perpendicular. Now I want to point out one more thing, which is because the slope of the straight line is negative a over b, then we should be able to pick 2 points. We should be able to pick 2 points P and Q on the line, so that the rise over run here is a over negative b. In other words, the vector QP will be given by minus b comma a, which I'm labeling as a. So then you can see that a, which is negative b comma a, is the vector parallel to L, and the vector n, if I take the dot product of n with a, then I also get 0. That's another way of knowing that this vector is perpendicular to the straight line L. So this fact then tells us that given the line, I can find a vector that's perpendicular to the line. So that gives me some idea that we may be able to write down the equation of a line by using a perpendicular vector. And after all, if you know a perpendicular vector, I mean, that's another way of kind of measuring the steepness of the line. So here is an example. Let's say I want to find the equation of the line passing through the origin and perpendicular to the vector n given by negative 2, 1. So I need to find the equation of this line. The question is, what do we mean by the equation of a line? Well, we mean an equation that will be satisfied by any given arbitrary point on the line. So let's pick an arbitrary point on the line. Let's call it, let's say this is an arbitrary point. Let's call it capital X, which is okay, so let's do it here. Okay, so how do we find it? Well, to find the equations, we're looking for an equation that will be satisfied by an arbitrary point on the line. Let's say capital X is an arbitrary point on the line. So x is x comma y. We want to find an equation that will be satisfied by xy. So then the vector OX, which is the position vector of the point X, so the vector X would be the vector OX. That's the position vector of the point X, and this would be x comma y. Clearly we can see that because the vector n is perpendicular so remember we are given that the line passes through the origin, and then n is a perpendicular vector to the line. So because n is perpendicular to the line, then we see that n must be perpendicular to x. So as a result, n dot product with x would be 0. So as a result, what we get is negative 2 times x plus 1 times y is equal to 0. So we are getting that y negative 2x plus y is equal to 0, or you can say that y is equal to 2x. So that the equation of the straight line is given by y is equal to 2x, which we can now verify that the line y is equal to 2x is a straight line passing through the origin, because when x is 0, y is 0, and also the slope of this line is 2, and the slope of the vector n is negative half, so clearly they are perpendicular. So you can see that, given a point, which was the origin in this case, given a point on the line and given a perpendicular vector to the line, we can write down the equation of the line pretty easily. So we're going to use this idea for it turns out that that's the general way of going about finding equations of planes. So let's say I have a plane, and I have a plane that where the plane passes. I'm calling the plane P. This is a script P, and let's say the plane passes through the point P, where the components of P are x naught, y naught, z naught, and let's say that the vector n, where the components of n are a, b, c, is perpendicular to the plane. And the goal then is to find the equation of this plane. So that is, we want to find the equation of the plane containing a given point P, x naught, y naught, z naught, with normal vector n is equal to ABC. So when I say normal vector, I mean it's a perpendicular vector to the plane. Okay, so we need to find an equation which will be then satisfied by any arbitrary point x, y, z on the plane. So let's pick an arbitrary point x, y, z, which I'm labeling as capital X. So I need to find an equation that will be satisfied by this point capital X, or the point x, y, z. Now notice if I look at the position vector of the point P, which is this, and the position vector of the point X, which is this, then the green vector Px would be x minus P. So remember a vector between, if you know the tail and the tip of a vector, then the components of the a vector would be the tip minus the tail. So I see that the green vector here, px, would be the same as x minus p. And clearly the vector n is perpendicular to the vector x minus p, because the vector n is perpendicular to the plane and the vector x minus p is parallel to the plane. So n is clearly perpendicular to x minus p. Okay, so because x minus p and n are perpendicular, since they are perpendicular, then we can say that their dot product is 0. So x minus p dot product with n would be 0. So x dot product with n, so here if we multiply out, we're going to get x dot n minus p dot n, and then p dot n can be moved to the right hand side. So we get x dot n is equal to p dot n. Now what is x dot n? Well, these are the components of x, y, z, and n is a, b, c. So if I take the dot product, I'm going to get ax plus by plus cz. And if I take the dot product of p and n, then I'm going to get ax naught plus by naught plus cz naught. So we see that ax plus by plus cz is equal to some constant d. Here x naught, y naught, z naught, a, b, c, those are given constants. So on the right hand side, whatever the right hand side is, I'm denoting that by d, which would be a constant. So the equation of the the plane is given by this. So what we have found is that the equation of the plane containing the point P with normal vector n is given by x dot n is equal to p dot n, where capital X is xyz, is an arbitrary point on the plane. And this can be written as, so this equation here can be written as ax plus by plus cz is equal to d, where d is ax naught plus by naught plus cz naught. One thing you need to realize is that the coefficients of xyz here, are the components of the normal vector n for the plane. Okay, so we have come up with the equation of a plane in the 3 space. So let's say I want to sketch the plane x plus 3y plus 2z is equal to 6. How would I do that? Well, to do that, I'm going to find the intercepts, the x and y and z intercepts. So notice the x-intercept would be, what would be the x-intercept? Well, to find, so the x-intercept of the plane is the point where the plane passes the x-axis. Well, so the x-intercept is a point on the x-axis, so y and z coordinates of the x-intercept would be 0. So if I set y and z to 0, then I see that x must be 6. So I get the x-intercept would be 6, 0, 0. Now to find the y-intercept, we will set x and z to 0 and solve for y, and we see that the y-intercept would be 2 because 3y is equal to 6, and then I get y to be 2. So the y-intercept would be 0, 2, 0. And lastly, to find the z-intercept of the plane, we set x and y to 0 and then solve for z, and you see that z would be 3. So I see that 0, 0, 3 is the z-intercept. Now these 3 intercepts, we will join them in straight lines, and then we get this triangular plane. So that's a portion of this infinite plane given by this equation. So of course the plane extends to infinity in all directions. So this triangular portion is part of this plane. So this is a nice way of visualizing this this plane. So this is the portion of the plane that is that lies in the first in this case only in the first octant. If we are given the equation of a plane, let's say x plus 3y plus 2z is equal to 6, and then we are asked to find a vector that is perpendicular to the plane or normal to the plane, then how do we do that? Well, the way we can do it is by reading off by making sure that, first of all, we need to make sure that x, y, z terms are on the left, and then we read off the coefficients of x, y, z, which are 1, 3, and 2. So n is equal to 1, 3, and 2 would be a vector that's perpendicular to this plane. Then it says find a point on the plane. Well, in order to find a point on the plane, any one point on the plane, you can set let's say x and y to be to whatever values you like, and then you solve for z. So if I pick x to be 1 and y to be 1, then in the equation, if I replace x by 1, y by 1, then I get 1 plus 3 plus 2z is equal to 6, and then I get 2z plus 4 is equal to 6, and then I get that z is 1. So I see that when x and y are 1, then z has to be 1. So 1, 1, 1 would be a point on this plane. Now there is nothing special about picking 1 for the value of x and y. We can pick x to be negative 1, y to be 9, and then we can solve for z as well. And we, instead of setting x and y, we could also set y and z to whatever values we like, and then we can solve for x. So to find just one point on the plane when the equation of the plane is given, the way to go is that you set two of the variables to whatever values you like, and then you solve for the third variable. So here's the remark that in r to the n, x minus p, so in r to the n, if I look at the equation x minus p dot n is equal to 0, or x dot n is equal to p dot n, this equation is set to be the equation of a hyperplane. So in r to the n, x would be x1, x2, dot, 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 xn. P would be let's say a given point in the n space, so we're calling it p1, p2, pn. These are coordinates, and then capital N is a vector in dimension n, a1, a2, dot, 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 an. Then this equation can be rewritten as a1 x1 plus a2 x2 plus dot 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 plus an xn is equal to some constant d. So if a point p in r to the n is given, a vector n in r to the n is given, then the equation of the hyperplane passing through p perpendicular normal to the vector n is given by this equation. So for example, in dimension 4, if we have an equation of the form 3x1 plus x2 minus x3 plus 2x4 is equal to 5, then this is a hyperplane with normal vector 3, 1, negative 1, and 2. So again, what we are trying to say here is that recall that the equation of a plane is given by this equation here. Now, if we take the same equation in dimension n, then that equation, the graph of that equation, is called a hyperplane. The straight line is called a two-dimensional hyperplane. So notice that in dimension 2 we have a linear equation like this. This is a straight line. In dimension 3 we have a linear equation, ax plus by plus cz is equal to d. That's a plane. And then if we go beyond, that is dimension 4, 5, and so on. So for example, ax1 plus a1x1 plus a2x2 plus a3x3 plus a4x4 is equal to d, then this would be a four-dimensional plane. However, it may look like, so this would be a plane in the dimension 4, or generally we call them hyperplanes. These are linear equations. It means that the exponent on each of the variables is exactly 1, and the coefficients are constant real numbers. Okay, so that's the end of my discussion on planes. In the next video, we will be looking at equations of straight lines in dimension 3 and beyond.